Welcome back everyone. My name is Sagar and we are back here with another video. So today is day 12 of our GeekStreak series and let's get started. So today we got the easy problem and it is BST to greater sum tree. So given a BST binary search tree and we have to transform it into greater sum tree where each node contains sum of all nodes greater than that node. So first of all, we are given a node of binary tree, binary search tree. That means binary search tree, then all the nodes that are right to it will have greater values and all the nodes that are left to it will have smaller values. So we just have to use that property and it is that simple. So what we have to do now, we are given a node of binary tree, root of binary tree, and what we have to do, we have to convert it, transform it into greater sum tree. Now what is greater sum tree? Greater sum tree means that node will have the value which is the sum of all the greater nodes. That means it is 2 and all the greater nodes are right to it. So 6 is greater than 2, 3 is greater, 7 is greater. So sum is 6 plus 7 plus 3, that is 16. So we have to do the same, so we have to replace 2 with 16, so this will be 16 and after that let us check for this. So this is 6 and all the greater values are right to it, so 6 will change to 7 and when we check to 7, so there is no greater value to 7, so we will just print 0. So this node will have then value 0 and for 3 we will have this plus this. So for 3 we will have 6 plus 7, that is 13. So we just have to find the pattern here, and that is when we are on the root node, when we are on any node, then we just have one confirm thing, that on the right side there are only greater values and we have to replace it with all the right side values. But is that the only case? No. As you can see in this case, so for 3 what values are greater? You can see 6 is greater than 3 and 7 is also greater than 3. So we can also find the similar pattern here. If we are on the left side, then parent will also have the greater value and the right to parent will also have the greater value than the left value. And same in this case, if we are on the 1, then what are the greater values? 2 and all the right values to 2. So for 1, what we have to replace? The value which was replaced for 2 and that was 16, because 6 plus 7 plus 3 is 16 and plus 2, because 2 is also greater than 2 and the value which is replaced by 2, that is sum of all right nodes. So 2 plus all the right nodes, that are 2 plus 16, so we have to replace 18 with 1. So the in-order traversal of this tree after transformation will be this: 1 will be replaced by 18 and 2 will be replaced by 16. So 6 plus 7 plus 3, 16. So for 3 we have 7 plus 6. So 6 plus 7, that will be 6, 13. And after that for this 6 we will print 7, and for 7 there is no greater value, so we will just print 0. So we don't have to print, we have to replace the value, that is transform the values, and you can see the transformated tree. So how can we do it? So we just have to generalize the thing we just saw. So for a node, what are the cases we have? How can we replace it? We can get all the right values, that is sum of all values that are greater than it. So for 2, 6 plus 7 plus 3. And we have also another case, that it is the left children of some node. So if it is the left children of some node, then we have to do two things. First, we have to store this 2 value because it will be transformed. So before transforming, we have to store that value. And also the another thing, that we also have to add the value that is from the right of 2. So how can we do it? So first I will just, okay, we have to make everything static. So static, I will create a sum that will store the sum of all right nodes, and for left children we will store the value of parent plus all the right values. So we will store in this variable, this global variable. So now what we have to do? First we will just initialize our sum with 0, and after that we will just create a recursive function that will contain our root. Okay. So now let's create that function. So it will be static2, static, and void dfs. You can name it anything. I just love that word dfs. And after that, first our base case. So what is our base case? So our base case can be this root itself is null. So if this root is null, if this root is null itself, then we will just return. We don't have to do anything. and after that first we will transform the right side of the tree. So for transforming we are using this DFS function. So first we will go to right side of the tree, and now what we have to do, so after this line this function will do everything for us. This will transform the right side of the tree, but now what we have to do, we have to change this value, that means transform our current root, and we know we are storing the sum of all the right values to our sum variable, that is a global variable. So how can we transform it? We can just replace the root data to our sum, but before transforming we have to remember that thing. Before transforming we have to store its value because we have to pass it to our left subtree. So before transforming, first I will store its value in some temp variable. So store the root data in our temp variable, and then we can transform our root. So I will change the root data to our sum. So after this point, our root dot data will contain the sum of all right trees, all right nodes. So for 2, we will have 6 plus 7 plus 3, and that is 16. And for 1, what we have to pass now? We have to pass this 16 plus this 2. So 16 is already stored in the sum, and we just have to add this 2, and 2 is stored in this temp variable. So 16 plus 2, then sum will be 18, and we have to just transform our left subtree. So root dot left, and that is it. You don't have to check for this thing, just have a recursive leap of faith. This function, this DFS, will do automatically everything for our right subtree. We just have to check for this root case, our right subtree is already transformed, and after that we just have to replace this value with our sum, because sum will store the all the values from our right subtree. So it is that simple. Let us compile it. So it is okay, and let's submit it now. And its space and time complexity required is O of n, and we are using O of n because we are just normally traversing through our tree, and if we consider the space of this recursive stack, then it will be log n, and this is constant. So that is it for today, everyone. If this video is helpful, go hit that like button and also subscribe to our channel, and let me know if you want these videos in English or Hindi or in both. So thank you for watching.